small. It's 5 parts in 100 million, the acceleration of gravity. So no, it is not about to rip the Earth apart. This is the tidal acceleration due to the sun. What else might exert a tidal influence on the Earth? Well, the second object that we might imagine would be the moon. Now, the moon is much less massive than the sun, but it is closer. And so, because of this third power of the distance, one might imagine that the tidal force generated by the moon might be comparable to that generated by the sun. And indeed, a simple scaling argument tells us that to get the tidal acceleration due to the moon relative to that from the sun, I multiply by the ratio of the masses and the ratio of the distances to the power -3. Plugging all the numbers in, I find that in fact the tidal acceleration due to the moon is approximately twice that due to the sun. So the dominant tidal effects on Earth are lunar tides rather than solar tides. But solar tides are not negligible. They are a 50% effect. The net result is a combination of the two. Let's take a look at what that does. So here we see the Earth and the moon, of course, drawn way too close to Earth to be to scale. And we see the elongated shape into which the moon is attempting to draw the Earth. Again, exaggerated way out of proportion. Remember, though, that while the Earth is rigid and unable to respond to this tidal pull, except very slightly, because it's a rigid rocky object, there's a soft component of Earth, namely the water. So the surface of the oceans will deform in this direction ever so slightly. Again, not to this extent, but there will be a high tide on this side of the Earth and a high tide on this side of the Earth and low tides at these points because of the tidal deformation that we discussed. And of course, as the moon orbits the Earth, the tidal bulge will point towards the moon, and as the Earth rotates once a day, each point on Earth will have 2 high tides and 2 low tides, and these, because you pass through these 2 points and these once a day, and because of the moon's motion along the celestial sphere, tides will repeat not every 24 hours, but every 24 hours and 44 minutes, because the moon advances by 44 minutes relative to the sun, remember? And so, indeed, if you look up tables of tides, you'll find the tides repeat every 24 hours and 44 minutes. This is because they are associated to the moon. But there is another effect another 2 effects that come into play. One is we can include the sun. So in this picture, the sun is way off to the right. The sun is attempting to extend the Earth as a horizontally extended oblong, whereas the moon attempts to draw the Earth to whatever direction points towards the moon. When the moon is full, Earth, sun, and moon are in line, and the sun's deformation, the moon's deformation, are in exactly the same direction. We get very, very exaggeratedly high tides. They're called spring tides. When we have a quarter moon, the moon is elongating the Earth this way and the sun this way, and the tides are diminished. We call them neap tides. Tides are very weak at quarter moon. And of course, when we get a new moon, again, the moon and the sun are elongating the Earth in the same direction, and tides are stronger. So tides are strongest at new moon and at full moon. Those are the spring tides. Tides are weakest at quarter moon. Those are the neap tides. And Newton's theory makes easy sense of all of that. And then there's another effect that we can take into account. The Earth rotates. What the Earth's rotation does is, as the moon creates a bulge of water, the rotation of the Earth, which is much faster than the moon's orbit by a factor of 30, remember, drags this bulge so that water that was raised here is actually over here. This means, farther to the east, this means that the high tide bulge is a little bit to the east of the moon, which means that high tide where you are is a little bit later than the time the moon crosses your meridian. It also has other implications, which we'll discuss momentarily. But these are the 3 effects that this demonstration shows very convincingly. To summarize what we've seen, the moon attempts to deform the Earth. It succeeds in deforming the water in the oceans, so there's a bulge facing the moon. As the Earth rotates, the bulge moves around the Earth, so everybody gets 2 high tides and 2 low tides. once every 24 hours and 44 minutes. So the time between one high tide and the next is in fact about 12 and a half hours rather than 12. The Earth's rotation drags the bulge to the east, so therefore it lags the moon. Like everything else in that image, the lag was way exaggerated. In fact, it turns out to be about 3 degrees or 12 minutes. Now, in addition to the moon, the sun exerts a tidal force directed towards the sun with about half as the strength as that of the moon. At full or new moon, these act in concert, creating the intense tides we call spring tides, which have nothing to do with spring. Whereas at quarter moon in either direction, the sun's deformation counteracts the moon's deformation, and you get the relatively weak neap tides. Cool, something we understand. Even more consequences of tidal forces. The moon is not able to deform the Earth, but when the moon formed a long time ago, much closer to the Earth, we'll see, and molten, it was soft and closer to Earth, and the tidal force of Earth, remember, at a closer distance with a mass bigger than the mass of the moon, you get more intense tidal forces. The tidal forces of Earth deformed the moon so that when it solidified, it froze with a permanent bulge. The moon is not quite round. Now, the tidal forces act to keep this bulge always aligned in the direction of Earth. We call this tidal locking, and this is the reason why, as I told you a long time ago, when we look up at the moon, we always see the same side of the moon. There is a near side and a far side to the moon. What locks the moon's spin period about its axis to its orbital period about the Earth is tidal locking, and this is a phenomenon we'll see before. Moreover, since the tidal bulge on Earth is being dragged to the east of the moon, the tidal force from the moon attempting to align the tidal bulge with the moon is actually trying to slow down the rotation of the Earth. Think about it differently. There is friction between the tidal bulge and the rotating Earth because the tidal bulge cannot keep pace with the rotating Earth. It's held locked 3 degrees away from the moon. What this is doing is it's slowing down the Earth's rotation. Yes, the Earth's rotation is slowing down. Look, but Ronan, what about conservation of angular momentum? Well, angular momentum is conserved. The way it's conserved is that that same bulge acts on the moon to, in fact, sling it faster along its trajectory so that the moon is being accelerated, and as it gains angular momentum, it's actually moving to higher orbits. So the moon is actually receding from Earth. This is an observation first argued strongly by George Darwin, son of the famous Charles Darwin, in 1898, and was the reasoning behind his theory that when the moon formed, it was indeed much nearer Earth. And as we will see, that coincides with modern theories. We think that the moon formed much closer to Earth. And these were conjectures until the Apollo missions left reflectors on the moon, enabling us to make a very precise measurement of the distance to the moon. And indeed, we can now verify experimentally that the moon is receding from Earth. So remember, it is now exactly the angular size of the sun in the sky. In a few millennia, total solar eclipses may be a thing of the past. So we've worked pretty hard, but we're getting somewhere. Understanding universal laws has given us a unified understanding of many, many phenomena. So we understand tidal forces, and remember, in space, nothing is held up. Everything is in free fall. Everything is in orbit around everything else. And so tidal forces are extremely important. This is very nicely evident in this beautiful image of M51, the Whirlpool Nebula. And what we see is that these are in fact two galaxies that are in the process of colliding. Galactic collisions are slow and rather delicate, but we see that there's a tail of stars from this galaxy being dragged out towards its neighbor by the gravitational force. And now that we understand tidal forces, it's not surprising that there is an equal tail being dragged out by the same tidal forces, since these are in free fall about each other. On the other side of the galaxy, tidal forces are approximately symmetric. These are falling in because the gravitational acceleration is larger than that with which the galaxy is falling. These because it's smaller. The net result is the galaxies being stretched in both directions. So understanding the uses and applications of F equals ma is a very powerful tool, and we're going to continue to apply it as we go along. And What we're going to turn to next is understanding a little bit more about the forces in nature beyond gravity, what else is there, and something about the M, something about the structure of the matter upon which these forces act. This will be important for understanding the structure and workings of various astronomical phenomena. And so that's what we'll turn to in the next clip.